Welcome to Microlecture 38 on E2 reactions and the mechanism of E2 reactions. Okay, so let's talk about some considerations that we need to think about when we're talking about eliminations. This time, as opposed to substitution reactions, we're going to be reacting our alkyl halide with a good base. That is to say, this is a species that's going to be attacking a proton instead of attacking a carbon atom as we did in substitution. We'll be forming an alkene. A carbon-carbon double bond is a product, and so major considerations here are we making the most stable possible product? And so recall that we know a lot about disubstituted, trisubstituted, tetrasubstituted, and even E and Z types of alkenes. And so whenever we're proceeding with an elimination reaction, we're forming an alkene, and we want to try to form the most stable product possible. So this is going to be a stability of products consideration. And so let's take a look at just a simple E2 elimination bimolecular reaction. One of our reactants is very likely going to be an alkyl halide. So maybe we have this, and we're reacting with not a nucleophile now, but something that would rather attack a proton. So like methoxide is a good example. And the proton that you want to look for is always going to be situated on the carbon adjacent to the carbon that bears the halogen leaving group. That's that one. You can call that the beta carbon, and you can call the hydrogen atom that's coming off of that beta carbon, you could call that the beta proton. You'll hear me refer to that as the beta proton. And so the base is going to actually go for the beta proton. And you're going to see that there's a beta proton here as well. But it turns out it doesn't matter which one it takes. In this case, I give you a pretty simple case. You would make the same product either way. So you can convince yourself of that in just a moment and kind of draw both mechanisms and both products out if you need. But the next thing that's going to happen after the oxygen-hydrogen bond is formed is the electrons that are in this carbon-hydrogen bond, this beta carbon to beta hydrogen bond, those electrons are going to break and kick in between these two carbon atoms, forming a pi bond. Okay, so a double bond is going to happen here between these two carbon atoms, and that of course gives the carbon connected to the bromine too many electrons. So we made a bond to carbon, we have to break a bond from carbon. And so there's actually 3 curved arrows for a proper E2 mechanism. Let's go ahead and draw the product then. Any region of the molecule that wasn't participating in the chemistry should just be redrawn. So I would redraw everything as the molecule is, and then just here is where the chemistry happened. We formed that pi bond, so it's now a carbon-carbon double bond. The O- has picked up a proton, so it's now an OH group, and that's methanol, CH3OH. The other product that forms is the bromide that was kicked out as a leaving group. So that is an E2 reaction. Now, the other product that could have formed if we had taken the other beta proton is actually the same. Okay, and so I'll just draw that out just to convince ourselves that if I had taken that proton instead, then what we would have ended up with is this. And if we tried to name these two compounds, what we would get is the exact same name. So take a moment and just convince yourself of that. There's only one product here. But it's often the case that we end up with more than one possibility for products. And so what about if more than one product could form? Let me give you another example here. Maybe I could have iodine as a leaving group, and we're reacting with KOH, potassium hydroxide. So a couple things that you can do to help yourself solve this problem is maybe to draw in any and all beta hydrogens that could leave as protons. Another thing you could do is wherever you see a potassium or a sodium, which are the most common spectator ions used, put a plus, and then you know whatever it's attached to is minus. And so now I'm thinking about this the right way. I know that I have a negatively charged oxygen atom, and that is a very strong base. So I'm going to go ahead and attack one of the beta protons, kick the electrons from the carbon-hydrogen bond in to form a carbon-carbon double bond, and lose my leaving group, in this case iodine. So this is the product that forms along with water. And that would be the same as if I had gone for the other side. All right, but there's still one other product if we consider stereochemistry. So in this case, we've formed the E alkene, right, or trans, if you prefer. And there's the other possibility that the R groups could be on the same side of the alkene. And so both possibilities are theoretically there. Okay, so the question becomes, do we form E or do we form Z? And we try to form the most stable product possible. So when predicting the major organic product here, we would predict E. If the question is draw the major organic product, then you would want to actually only draw this. And be careful to not draw any other product that is exactly the same thing. So we would never want to say, you know, that both of these alkenes form, because they're exactly the same. So there's one major organic product for this reaction. Let's do another one. Let's say that we start with this alkyl halide. Say we start with this, and so we're using a sodium methoxide, and so again, wherever you see a sodium or a potassium, put a plus charge, and you know whatever it's attached to is negatively charged. Then you know what your strong base looks like here. It's got a full negative charge on oxygen, and it's ready to attack a proton, as bases do. So I'm going to draw in all the possible beta protons here, and see, you know, we have a few choices. If my job was to draw the major organic product, then I would be thinking a lot about stability of the possible alkene product. And so I could form the double bond right there, or I could have chosen one of the other beta protons and formed the double bond right there. And these are actually the E alkenes. So there's the other possibilities here, that we could have formed the Z alkene. Right. So we already suspect that E would form over Z, but which of the two E forms would we consider to be the major organic product? Take a moment here and think if we've talked about any stability rules that might allow you to pick which of the two E forms would be more stable. And so if you said conjugation, you're absolutely right. We have more alternating double bond, single bond, double bond, single bond going on right here. And that's going to make that structure our major organic product among all of the possible alkenes that could form. And so that's an electron delocalization argument or conjugation argument. If you were asked to explain why you chose that as your major organic product, you would have to include an argument that involves electron delocalization, which leads to stability.